this lecture we discussed about two elementary types of flows. One is a uniform flow, another is a source or a sink. Let us try to now make an analysis of whether we can superimpose these types of flows. So, let us take an example which is example 3 for us. Uniform flow along x axis plus source at x equal to 0. Okay. So, the physical picture is you have uniform flow u infinity and then at origin you have like this, say q is the strength of the source. So, by looking into the flow, can you say that whether there is a possibility of a stagnation point somewhere, that means the velocity is 0. See, this is going towards the negative direction here and this is going towards the positive direction. So, somewhere these two should cancel, so that along x axis you have a chance of getting a stagnation point. So, the first observation is that you have a chance of getting a stagnation point along the x axis or on the x axis. So, what is f here? F is equal to f1 plus f2. So, f is u infinity z plus q by 2 pi ln of z. Okay. So, what is df dz? Okay. So, this is u infinity, so this is u minus iv. Okay. You can express also in terms of r theta coordinate, sometimes because there is a source it is easier to express it in terms of r theta coordinate. So, it is u infinity e to the power I theta minus q by 2 pi r e to the power minus I theta, right. So, why we have written it in this way? Because this will be now Vr minus I v theta. So, what will be Vr? U infinity cos theta minus q by 2 pi r. And V theta is, what is V theta? V theta is minus u infinity sin theta, right. at the stagnation point both Vr and V theta are 0, right. So, our objective first is to find out the stagnation point, the streamline passing through the stagnation point which is called the stagnation streamline, because the streamline passing through the stagnation point will represent the shape of the body past which this is the resultant flow. Okay. So, at the stagnation point you have V theta equal to 0, so a plausible stagnation point from physical point of view. So, where it will be located? It cannot be located in the right side, right, it can only be located, it cannot be located also, so it can be located only in the left side of this origin where this negative flow and the positive flow can cancel. So, that left side or the negative side of this is represented by theta equal to pi. So, and Vr is equal to 0 means u infinity cos pi, that is minus 1 I think I have made a mistake here, this should be plus, right. Yes. So, it is just striking while this minus sign is coming here. So, df dz is u infinity, but this is just plus. So, with the inertia of this minus I wrote a minus here, this is plus, just correct it. So, this should be plus, that means this should be plus, that means this should be plus, right. So, minus u infinity plus q by 2 pi r equal to 0. So, q, so the r will be the radial location. So, why it struck to me that it cannot be negative is that r is the radius vector, it itself cannot be negative, right, r has to be positive always. So, r is q by 2 pi u infinity, right. So, roughly speaking this is the x axis, this is the origin, from the origin what is the radial distance? Q by 2 pi u infinity, right. So, from the origin and on the x axis with theta is equal to pi. So, this is the stagnation point. So, once you have the stagnation point, let us try to obtain the stagnation streamline. So, you have f so u infinity r e to the power I theta plus q by 2 pi ln r e to the power I theta. right. Just somehow I am trying to extract psi from here. So, this is u infinity r e to the power of I theta is cos theta plus I sin theta plus q by 2 pi ln of r plus I q by 2 pi theta, right. So, this is nothing but phi plus I psi. So, now if you isolate the real and imaginary parts, the psi will be u infinity r sin theta plus q theta by 2 pi, right. This is psi. So, what is the shape of the body? The shape of the body past which this is the representative flow, uniform flow plus a source here, that shape will be governed by the streamline which passes through the stagnation point, because stagnation point is also located on the body. Okay. You may argue that if you have a body like this, just as an example, if this is the stagnation point, why other points are not stagnation point? Why all the points on the body are not stagnation point? This is the very interesting difference between the real viscous flow and potential flow. In the real viscous flow, all the points on the body have no slip and no penetration boundary condition. Okay. So, no slip comes from the considerations where viscosity plays a very critical role, and no penetration is a kinematic boundary condition. It comes from the body contour, fluid cannot penetrate through it. For a potential flow, the no penetration boundary condition is there. So, this no penetration is much more fundamental than no slip. It has to be there no matter whether it is irrotational or rotational flow. What may be violated is the no slip boundary condition. So, that means all points on the body will not have 0 velocity, although it will have no penetration, but it may have slip, except the stagnation point or the stagnation points. There may be multiple stagnation points where you have both the components of the velocity 0. So, that is why stagnation point is so special in a potential flow. Now, the shape of the body, whatever may be the shape, it should pass also through the stagnation point, because stagnation point is one of the points where the flow is to a standstill. So, where we were, the stagnation streamline, if you define the stagnation streamline, say psi equal to psi s, you define that as a stagnation streamline. So, this is equal to u infinity. So, let this r be equal to, let us say this is equal to a, u infinity a sin theta plus q theta by 2 pi. So, this theta is pi, right. So, this becomes 0 and this is q by 2. So, that means u infinity r sin theta plus q theta by 2 pi is equal to q by 2. This is the equation of streamline passing through the stagnation point. See, mathematically you can write this equation. It is always interesting to physically try to imagine what kind of shape it will be from the equation. This is very, very important, and I will say that this is a priceless skill, and this is where the educational paradigm is shifting from the time, say possibly when we were high school students to now. So, when we were high school students, we were always encouraged that given a mathematical function, how do you sketch it, how do you visualize it, and nowadays given a mathematical function, a student has a software, immediately plots it in a software and then gets a picture. So, it is completely missing that I mean this how to speculate the shape of the curve line whatever from the equation. So, now we have our equation q by 2 is equal to u infinity r sin theta, where is that, this one, psi equal to psi s, u infinity r sin theta is y, straight away I am writing y, plus q theta by 2 pi. So, u infinity y is equal to q by 2 into 1 minus theta by pi. So, y is equal to q by 2 u infinity to pi minus theta by pi. Right. So, what does it tell you actually? Substitute different values of theta, just substitute different values of theta. So, you substitute a value of so first of all, what does it say, this curve, this passes through this point, what about what happens as x tends to infinity? Does it somewhere close the curve by passing through the x axis? That means, do you have somewhere where y is equal to 0? Yes, only this point, but on this side, see, except for theta is equal to pi, nowhere else y is equal to 0. That means, this curve does not pass through the x axis again except at this point. Okay. Number 1. Number 2 is, this curve is symmetric with respect to x axis, right. So, you have this y coordinate. So, just you change theta from say so just put theta equal to say pi by 2. Okay. So, when you put theta equal to pi by 2, actually I should put it here r sin theta to make it instead of y, because then there are theta at two places, that will make you understand it better. U infinity r sin theta. So, let us take theta is equal to pi by 2 as an example. So, when theta is equal to pi by 2, u infinity r is equal to q by 2 u infinity okay. So, in this way if you get points with different r and different theta, you will see that this body, so symmetry with respect to x axis, how do you check? So, this is just how to get points on the body, but how do you check whether this body is symmetric with respect to x axis? Directly x is not coming out here. So, you think about it, but the way in which this curve will be is something like this. So, you can do all the checks that how it will be like this by finding out what is the, so you can write, sometimes writing in terms of polar coordinate is little bit difficult in terms of visualization, you can write it in terms of regular Cartesian coordinates. So, then you can write this theta as either tan inverse y by x or something like that, and then see what happens. This is very important, how this shape can be obtained. What happens as x tends to infinity? So, if you find out the x tends to infinity, you will find that the slope of this curve will be tending to 0. So, the asymptote will be parallel to x axis both for plus y and minus y, and that will actually result in a shape like this. This is a beautiful shape which is generated, this is called as a half body or Rankine half body in potential flow theory. So, the streamlines will be something like this. There will also be inner streamlines, but this entire exercise is actually to mimic flow outside the body. So, inside what happens is, inside you will have this source and then uniform flow, something is happening with the superposition, all these things, but what is matter of importance is what is the shape of this body, and at any given theta this y, this h you can obtain by using this formula. Okay. So, when theta is equal to 0, all lines on this x axis will correspond to theta equal to 0. So, when theta equal to 0, you will see that it is asymptotically attaining a height which is q by 2 pi u infinity. You put theta equal to 0, you will see that this asymptotic height is recovered, that is the height of the body. All these geometrical parameters are important because these parameters can only tell you what is the shape of the body past which the flow is generated by this arrangement. We will consider another superposition and then we will call it a day today. So, this was what example 3, we will consider example 4. Source of strength Q at x equal to minus epsilon plus sink of strength Q at x equal to plus epsilon, where epsilon tends to 0. We will start with this example today, maybe we will not be able to finish this and we will take it up in the next lecture. So, the physical picture is there is this is the origin 0 comma 0, this is epsilon comma 0, here you have sink, sink means all flow is coming to it. This is minus epsilon comma 0, here is source, okay. So, now what is the complex potential? Superposition, source at this q by 2 pi ln, shift of place from 0 to minus epsilon, see it was ln z minus a. So, z minus minus epsilon, and here it is sink of the same strength. So, q will be replaced by minus q. So, we can write q by 2 pi ln z plus q by 2 pi ln 1 plus epsilon by z minus q by 2 pi ln z minus q by 2 pi ln 1 minus epsilon by z, right. So, this gets cancelled. So, q by 2 pi, we can expand this in a logarithmic series if epsilon is small. So, ln of 1 plus x is x minus x square by 2 plus x cube by 3, in this way it goes, minus q by 2 pi just replace epsilon by z by minus epsilon by z, but square term is plus minus is independent, right. So, you can clearly see that this epsilon by z gets, sorry, it does not get cancelled, I am very sorry, the square terms gets cancelled. So, what should I do? I should keep a tick, so it remains, this is what gets cancelled. this one and this. Okay. So, these terms remain. So, f is equal to q by 2 pi into 2 epsilon by z in the limit as epsilon tends to 0. So, q epsilon by pi z. Just in a shorthand, if you write m is equal to q epsilon by pi, then f is equal to m by z. This is the new potential that we have realized if we bring the source and the sink very close to each other, and this is called as doublet. What kind of body it generates, what kind of streamlines it generates, what kind of potential lines it generates, that we will see in the next lecture. So far we have looked into uniform flow, source, sink and half body, and now doublet. Doublet we have not completed because it requires a good inspection of the potential and the streamlines to get a picture of the flow field in a doublet, and that we will do in the next lecture. Thank you.